The last type of graph is the acceleration time graph, which we're not going to look at that closely, but I still wanted to make these same examples in the acceleration time graph so that if you ever find it, you'll know what to do with it. So again, our x-axis is time. So it's always time, but the y-axis is the one that changes and that you have to look at carefully. Acceleration. The unit for acceleration we haven't seen yet, but I'm going to tell you right now, is meters per second squared. So it's close to this one, but there are 2 seconds at the bottom, so it's per second squared. We'll see that next class better. But okay, so I do the same thing. This is 0 seconds, 2, 4, 6, 8, and 10 seconds. And here, let's say we have 1 meter per second squared, 2 meters per second squared, 3 meters per second squared. Okay, so now how do we transform these lines to an acceleration time graph? So our first example was at rest, not moving. The speed was always 0. The speed wasn't changing. Since acceleration is the rate of change of speed, there was no acceleration because the speed was not changing. So we're just going to get a line here at 0. So it looks the same in both speed time and acceleration time graph because the speed is not changing and the acceleration, there is no speed and there is no acceleration because the position is not changing and the speed is not changing. So that's at rest. Now what about these horizontal lines? So these ones have a constant speed, That means that speed is not changing either. So we're going to have, again, no acceleration. So if we have a horizontal line here, we are going to have a line again at 0 here. So it's the same line because the speed is constant. So here we basically have a constant speed of 0. Here we have a constant speed of 1 and here a constant speed of 2. So the 3 lines are going to be a horizontal line at 0 because speed is not changing, so there's no acceleration. So our 3 examples are here. Now here we do have an acceleration. The speed is changing because the line is going up. So the acceleration we're going to see, we can calculate it as the change in velocity over time, so v over t. So here we had that it went from 0 to 4 in 10 seconds. So that is an acceleration of 0.4 if I use this equation. So I'm going to have a line here in 0.4. And that is actually the slope of the line. What I did here was calculate the slope of the line. So while speed is the slope of this graph, acceleration, let me use this color, speed is the slope of a distance time graph, and acceleration is the slope of a speed time graph. Acceleration is the slope, right? So if we find the slope of this line, it'll give us 0.4, which is the acceleration of the object. And what about this line? So decelerating means it has a negative slope because the change in velocity was not positive 4. The velocity didn't increase from 0 to 4. It decreased from 4 to 0. So the acceleration in this case is going to be negative 0.4. So what we're going to have is we're going to need to extend our y-axis to the negative numbers, put here negative 1, and we're going to have a line that is down here at negative 0.4, right? So basically what we have here is that all of at rest or constant speeds, whichever that speed is, constant speeds are lines at 0. Acceleration are horizontal lines above the 0 line, so positive accelerations. And deceleration are going to be graphs, horizontal lines below the x-axis because they're going to be negative accelerations. So we had these lines. If we calculate their slope, we get the number that we need to put here in the speed graph. So from this one to this one, we go by calculating the slope. And from this one to this one, we go by calculating the slope also. So the slope of these lines are going to give us the value in the acceleration graph. But we can also go the other way around. So we're not going to practice this yet. We're going to look at that later in the year. But still, I wanted to mention it. The way that we go from here to here and from here to here is calculating the area. So if I calculate the area below the line, which you're going to see sometime in math. So for example, if I wanted to calculate the area of this orange line on top, I would calculate this area that is between the line and the 0. So everything I shaded, this, all of this. This area is going to give me the speed. So that is how I go from this graph to this graph. So in this graph, write that in blue. So from here, area is the speed. And we can do the same thing here. So if I wanted to calculate how much distance was covered by this orange line to make it more interesting, I would calculate this area, which is the area of a triangle, right? Because this makes a triangle up to 10, right? So it's the area of this triangle. So this area in a speed time graph, the area is going to give us this graph, distance. So area is distance. So it's okay if you don't understand that well, or if you don't know how this applies, that's okay. I just wanted to mention so that you know that going from here to here you use slope. From here to here you use slope. But from here to here you use area, and from here to here you use area. That'll make more sense in the future, but that is the introduction that I wanted to give you to graphs about linear motion.